Hey guys, I'm starting to work down in this area, and I immediately noticed something kind of interesting, I thought. This resistor, body and dot. That's how you read these dog bones. So the body color is white, the end color is also white, and we got an orange dot. First two are the first and second digits, and then the third is the multiplier. So white is 9, so we have 9, 9, and then 3 zeros, 99K. Alright, fine. Here it is on the parts placement. It is number 35. Okay, and what do they have for that? White, white, orange. Cool, but it says 0.1 meg, also known as 100K, which would be brown, black, yellow. And on the schematic, they show it as 0.1 meg or 100K. So what they're basically telling you is that even though the color code is white, white, orange, which as we all know is 99K, they're saying it's actually 100K. Now I've heard it said that the reason Philco chose these parts values was so that the workers could easily identify them in the lighting conditions found in the factory. I don't know if it's bad lighting. I think it was more likely the type of spectrum that the lights put out. Maybe they were an early type of fluorescent to save on the electric bill. I don't know. But that's the first time I've seen that on the other Philco schematics. Yes, they were oddball values, but they would say they were 99K. They wouldn't just flat out like deny reality that it's actually marked as 99K, but really we're going to call it 100K. So what am I going to put in there? Well, I'm going to put a 100K, because 99K isn't exactly a standard value these days. And apparently that's what they label it as on the schematics. That's really what it's supposed to be. Or maybe they were using up old stock of these. I don't know, but I'm kind of curious that the parts list clearly says it's a 99K, but the value specified is 100K. I just finished up with that bake light block. Now I'm moving on to this one. I'm finding it easier to undo the wiring and work on them outside the radio. Now what I found out on this one was what was going to this side lug. No internal connection for it. It's just uses a tie point. A 10K resistor, which is this guy on the schematic, number 32. One side goes to the volume control, the other side goes to the tone switch. Well, there are two internal capacitors on that tone switch and then one direct lug. So here's that red wire that was going to the bake light block going into this, which has two capacitors buried inside of it. And then here's a wire that was going directly to the lug on the switch. All three of those are going to the side lug. The black wire, the red, and the resistor. But look at this black wire. It snakes around here and then it's going to this. It's just simply looped around here, no solder, no other components or anything, and then it continues on to the switch. Now this sure looks like a ladder addition, and it's not shown in a parts locator, and it doesn't appear to be doing anything. All I can figure is it was part of an old potential modification that never happened. Maybe they were going to bypass the capacitor inside here and attach one somehow, or put some other components in here. Well, what I intend to do is take this wire out, replace it with one that doesn't have a break in it, and just take this out. It's not doing anything. Strange. So all that's inside here is a single capacitor. I'll just dig that out and then wire this back in. Now the other wire going to this tone switch, the insulation is really crumbling. Both of these appear to be natural rubber. I don't know how the red one survived so well and the black one didn't. But I'm also going to be digging in here to replace those caps inside. So while I'm doing that, I'll just run two new wires. And I'll try to preserve all this original as best I can. How they have it wrapped around here could very well be to prevent noise from getting in there. Do as little moving around of things as possible. I knew things were going too well. I just hit a major snag. The driver transformer has an open primary. I already popped it open in the hopes of finding a break in the wire somewhere, but no luck. No luck there. So one of the fine wires here, and here's the other. Maybe still possible to find the break. I don't know. I could pop this core out. I could start unwinding it, but I'm really not sure at this point even there's a primary on the inside or the outside, and I could try rewinding it, although it's not something I really have any experience with, and I don't have any wire of this gauge. But all may not be lost, because I just saw a little trick online. So here's the transformer right here. So the primary is driven by a 42, and then the output is tapped that does the phase inversion and drives the 42s. So it's this side that's open. The secondary looks fine. So if we could just get a signal somehow into this transformer, it could still work. Well, it so happens that it is possible to do it. If you disconnect the primary entirely, which means you won't get any power going to the plate of the driver tube. So this is going down to B plus here. What you do instead is use a resistor to provide that B plus, and then you tap the signal out using a capacitor. And by doing that, I guess the signal goes straight through here to that grid, and then does phase inversion and goes to that tube. Now this is with 71As and a 27. However, these 42s are wired up basically as triodes, where they connected the plate to, I think that's the screen there, and they're just driving the grid, so they're just acting as triodes. Same goes for this guy. So it's certainly worth a shot. I don't think this value of capacitor is critical. This we can experiment around with, but I can certainly start out with 27K and see how it works. Now, I've heard that this actually can work better than the original, get a fuller response. Also, there was another trick that even if this was working, suggestion was to put a capacitor in here to and use a resistor to drive the primary to prevent DC current going through here, which is what burns these out. Here's what I'm talking about. So instead of having B plus going to the primary, ground that, feed it with a capacitor, and power the plate through a resistor. Help save the life of this transformer, and again possibly improve the frequency response. I'll post a link to this in the video. So now I'm going to have to put this thing back together and tidy it up to try that out. Trim off those broken ends, tape this back up, and put the core back together. It's actually pretty easy to get apart. These are E laminations, and then there were I on the other side. And they weren't alternating. I've seen some where every other plate or group of plates, they have the E's going the other way. But in this case, they were all the I's were on one side, so all I had to do was give it a little tap, and they just all broke off. So I got to put them all back on, and then put one of these guys at either end to squeeze and hold everything together. Here are the secondary leads. Go up here, got to make sure that they are all still having continuity if I want to try this trick out. If all else fails, well, I can get a replacement driver transformer like I did with the Stromberg-Carlson 64 project, or there's also a solid state possibility, which I tried making and I did experiment with a little bit, but I could not get it to work. Now, it's entirely possible it's because I just tacked these leads together and left them full length, and it might have been causing some feedback or oscillation, so I can try making this a little bit neater. This was posted in a magazine a while back, and they had versions for both single-ended and push-pull. It's a solid-state transformer replacement, It does the phase inversion with high voltage transistors. But yeah, I had trouble getting it to work, but I could certainly give it a try. And if I do this a bit neater, it would fit inside this can. But first I'm going to try just driving the secondary of this and bypass the primary.